Hello, everyone. My name is Detai. I'm now a second-year graduate student with the Saruwatari Lab Graduate School of Information Science and Technology, the University of Tokyo in Japan. Today, I'm going to talk about cross-lingual speaker adaptation using domain adaptation and speaker consistency loss for text-to-speech synthesis. This paper will be presented at the Interspeech 2021 in Brno, Czech. Okay, let's get down to the main topic. Here is the content of my presentation. I will first introduce the background of this research. I'd like to explain the motivation of this work. So first, what is cross-lingual TTS? It refers to a task that requires a TTS system to synthesize source language speech for target language speaker. For example, in this work, we synthesize English speech for Japanese speakers while maintaining their voice characteristics. Generally, we don't have English speech data for Japanese speakers. This diagram illustrates a typical method for cross-lingual TTS. Basically, we use speaker and language embedding to train a multilingual multi-speaker TTS model. Then we change the language embedding to synthesize the speech of the target language of the same speaker. However, we cannot always have such model from the aspects of data and computational efficiency. Since first, some lower resource languages may not have enough data to train a TTS model, and second, the computational cost will increase dramatically with the increasing of language number. In such case, speaker adaptation can be used, which refers to a technology that can adapt a pre-trained English TTS model to a new English speaker with relatively lower cost. Generally, we only need 1 minute speech data to adapt it to a new speaker. In cross-lingual speaker adaptation, we instead need to adapt it to speakers of different languages, like Japanese or something except the source language. The idea of typical monolingual speaker adaptation methods is fine-tuning the pre-trained TTS model using the new speaker's data. However, it is hard to fine-tune the TTS model using cross-lingual speech data. The core idea of this work is doing cross-lingual speaker adaptation for TTS using transfer learning. Our basic idea is inspired from previous monolingual speaker adaptation method using transfer learning from speaker verification to speaker adaptation. In such a way, we only need to train a multilingual speaker verification model and a monolingual TTS model. The knowledge saved in the speaker encoder can be transferred to the TTS model. As a result, the proposed method has higher computational and data efficiency. I will now introduce the baseline method, which is a monolingual speaker adaptation method. This method includes 3 steps to do speaker adaptation. First, we train a speaker verification model on multilingual data. Then, we train a TTS model on the source language's data using the speaker embedding generated by the speaker verification model. Note that in this stage, we freeze the parameters of the speaker verification model. And finally, we adapt the model to a new speaker by using the speaker embedding of her to synthesize the speech. Specifically, in this work, we train the multilingual speaker verification model using GE2E loss, which is an effective loss for speaker verification. We then train a monolingual multi-speaker tachytron 2 model by conditioning the model on the speaker embeddings generated by the speaker encoder. Next, I will introduce the proposed method. The baseline method has 2 problems. First, the domain shift is easy to appear in a multilingual speaker verification model. which makes it harder to adapt to cross-lingual speakers. Second, we cannot fine-tune the TTS model on cross-lingual data. We then extend the baseline method to solve these problems. We first use domain adaptation to train a language-independent speaker encoder. We then propose a speaker consistency loss to fine-tune the TTS model on cross-lingual speech data indirectly. We use domain adversarial neural network to obtain a language-independent speaker encoder. Specifically, we add an adversarial language classifier in the baseline speaker encoder. This classifier will exclude any information relating to language from the speaker embedding using the adversarial training. The speaker consistency loss utilizes the knowledge of the speaker encoder. For any speaker, we first generate her speaker embedding to synthesize the speech. We then feed the synthesized speech to the speaker encoder again to get the synthesized speech's speaker embedding. Finally, we maximize the cosine similarity between the two embeddings. We use the SCL to fine-tune the TTS model. This figure illustrates the training procedure of the proposed method. We first train a speaker encoder based on multilingual speaker verification. Then we train a TTS model using monolingual speech data. In this stage, the parameters of the speaker encoder are frozen. Finally, we use both the monolingual and cross-lingual data to fine-tune the TTS model. In the fine-tuning stage, we freeze the parameters of the text encoder of the TTS model and the speaker verification model. Finally, I will describe the experimental results. The experimental conditions are listed in this table. We used multi-speaker English dataset with ATK and Japanese multi-speaker dataset JVS to train the model. The total speaker number is 207. We picked up 16 speakers from the datasets as the unseen speakers. We used the 80-dimensional Mel spectrogram as the acoustic features fed into the speaker encoder. For English, we used the alphabet as a text representation. Note for Japanese, the target language, we don't need text data, though JVS has it. We trained 4 models for comparison. The baseline model and the proposed model are denoted by base and DA plus SCL, respectively. For ablation experiments, we also trained 2 models, base plus SCL and DA. Note that for the 2 models without SCL, namely base and DA, there is no fine-tuning stage. Besides, since SCL is used only for TTS model, there are only 2 speaker encoders with or without domain adaptation denoted by base and DA. We conducted both objective and subjective evaluations. To evaluate the language dependence of different speaker encoders, we train a new language classifier on the embeddings generated by the 2 speaker encoders and compute the classification accuracy. We also used a randomly initialized speaker encoder as a control model. As you can see, the speaker encoder using domain adaptation obtained the lowest accuracy, which shows that the language dependence is eliminated by using unsupervised domain adaptation. We also visualized the speaker embedding of the natural and the synthesized speech. You can see that first, the domain shift is obvious in the base model. Second, the SCL actually makes speaker embeddings of nature and synthesized speech closer. In the subjective evaluations, the speech naturalness is evaluated by standard MOS test, which is conducted on Amazon Mechanical Turk. You can see in this table that the DA plus SCL model obtains the best performance. If we focus on intralingual tasks, we find that models using SCL obtain the best performance. But if we see the cross-lingual tasks, you can see that the base plus SCL model has poor performance. This demonstrated that the knowledge saved in the language-dependent speaker encoder is not suitable for cross-lingual speaker adaptation. We also conducted XAB test to evaluate speaker similarity. In most of the cases, our proposed method obtained better performance. For the cross-lingual unseen task, the proposed method have comparable performance to the baseline method. We assume that this problem is due to the small amount of data used in the speaker verification model. Actually, typical speaker verification model will use thousands of speakers, but in our experiments, we only used 200 speakers. Here are some analyses. As I mentioned, our proposed method obtained significant improvements on speech naturalness and comparable speaker similarity. The base plus SCL model have poor performance on cross-lingual tasks, which demonstrated that the language-dependent speaker encoder is not suitable for cross-lingual speaker adaptation. For the time reason, I will not show you the audio samples, but you can find them on our project page. Besides, we also trained 2 new models. The first model uses about 700 speakers to train this speaker encoder, which is about 3 times of the data used in the previous experiments. The second model is trained by augmenting the speaker encoder with another task, gender classification, which can help the TTS model to avoid gender errors in the synthesized speech. Although we haven't conducted evaluations on the new models, you can also find the audio samples synthesized by them on our project page. To conclude, in this work, we proposed a cross-lingual speaker adaptation method using domain adaptation and speaker consistency loss for TTS synthesis. Our method makes it possible to fine-tune the TTS model on cross-lingual speech data. Our method obtained better speech naturalness and comparable speaker similarity in the subjective evaluations than the baseline method. The experimental results also indicated that using a language-dependent speaker encoder to fine-tune the TTS model will instead cause performance degradation. That's all. Thank you for your attention.